我们就开始了。我看一下。OK， 有人在录。Okay, so welcome everyone. Today, we're going to learn some referencing language and coreference resolution, which is like new sub. I would say it's kind of like a sub NLP model, which is commonly used across very different like tasks and also many different models. So the outline or the plan for today's lecture are actually follows like this. So the first kind of like part, we're gonna give a little bit of brief introduction on what coreference resolution actually refers to. And then we're going to talk about some kind of applications of coreference resolution. And next, we're going to talk about some mention detection, techniques. And in the next part, we're going to talk about, different type of references. Actually, there are four kinds or four different types of coreference resolution models. Later, we are going to introduce. Starting from 5, which the first one, which is handwriting algorithm, which is called Hobbs algorithm. The second one is called mention pair model. The next one is mention ranking model. The next one is mention clustering model. And at the end, we're going to talk about, a little bit of introduction on the evaluation on how actually, different models perform. And also we're going to introduce some kind of like, results comparison across different models on which model actually is the best, which is the worst, and which one can be used as a baseline. So I think Yu Yao is going to cover from point 1 to point 6. So she's going to cover this part. So I'm going to cover the last 3 part on the model part. So I guess now is actually Yu Yao's stage. Up to you.
Hi everyone. Let me share my screen. So everyone can see my screen?
No, yeah, I guess I have to stop sharing my screen.
Oh, yeah.
Just 1 second.
Yeah, I think that works.
Yeah, it works.
Okay, great. So we come to the first part. What is the coreference resolution? So let's read this sentence. So Barack Obama nominated Hillary Clinton. So this whole sentence, when we go through this, we will find out, okay, there are some like nouns like Barack Obama and Hillary Clinton, and here his, and also he. So we find so many pronouns we identify as mentions in our word, in our words context. So here, so yes, we mark all those mentions, and then we group it. So here, the red words here, they all refers to same thing. So it's the Barack Obama. So it's identified as same people, same person. Same as here. So Hillary Rodham Clinton, we identify all those orange words as same thing. So this is this lady. So all those mentions in orange color, since they refers to the same person, we will identify all those orange words, letters are coreferent with each other. So that's the meaning of the coreference. So yes, we have a, so for a human being, to identify those words refers to same person is so easy and quick, but sometimes take a while, take a look of this long paragraph. So they have so many, the Vanija, like so many names, and also here, they, and also her. So those words, I just changed to this page. Oops. Yes, we just mark all those words, you see, all those Adhila and they and her. So her here means the Vanija when we read the whole paragraph. And they here refers to the Akila's song and her song as they. So for us, it will take a while to identify those coreference, but for the machine, they can identify kind of like a one-to-one, like a pair. For example, Phoenicia, they were here is like she is refers to a Phoenicia, but for they for two pairs with one refers, the machine probably cannot identify that. So kind of like, well, when we train our models, the target is find out all those coreference words. So here's application. For example, we have a full text or full context book. So we need to find out the information. We need to find out what's the summarization of this paragraph. So then we need to find out, okay, what he, she, they, or it, those words mean, what's the reference for? For example, he was born in 1961. So what is he means here? So we need to find out. And we'll explain later how we find out what is he means here. Also for example, the Google translation. So Alicia liked John because he is smart. So Google Translator help us identify. He means John is a male. So he put he instead of it or instead of she. So for Google Translator, they already built in a coreference identify system, help us like show what is the he means here, what is he referred to Juan. But for some other languages, you see, like instead of the Spanish, some language, they don't have a gender, very clear line of gender or of numbers. So here when we do translation, you see, it's like a similar sentence. You should sometimes put she, sometimes he put he. It's not that correct. Also for this kind of like chat system, we also can apply that as well, apply this coreference system. So here is a chat. So James Bond is the actors of a movie and the Spectre is the name of the movie. So actually these two red words is linked together. They have a kind of like a coreference kind of link with each other. So for our coreference system, we need to identify James Bond and the Spectre is one group, is one cluster, and they are linked together. This are all the like a coreference system useful just to find out the link, the relation between two words. Sometimes it's the pronouns, sometimes it's the nouns. Okay, so how we use our coreference resolution system? They have two steps. The first step is we need to identify all the mentions, all the like pronouns, nouns, like all this kind of keywords in our sentence. Oh, someone. Can you mute everyone? Daniel, could you help me to mute everyone? It seems. Okay, no, that's great. So here, for example, this sentence here, I, neither, he, my, she are all the mentions. So the second step is after we detect all the mentions, we need to cluster them. So when we read this sentence by our human being's brain, we'll see he refers to neither, and I, my, she is another group, which refers to same person. So basically it's two steps for our coreference resolution system. And there have three kind of mention detections. One is the pronouns, like as we know is I, your, this kind of words. And another is a named entity, like people, place, like kind of like it's a named entities. Another one is the noun phrase, like this sentence, the cat and tree, these are noun phrases. We need to identify them and find a relation between each other. So there's so many ways to kind of like tag our detections. For our pronouns, we use the POS tagger, And the name entity, we use the named entity recognizer. I think we in the class we explained in the last few classes. And the third one is for noun phrases. We'll explain later. Kind of constitutive parsers, which is identify different nouns by the meaning of these words. Sometimes it's not that simple because, for example, it is sunny, so we identify it as mentions, but basically it don't have any meanings. It's just the beginning of a paragraph or of a text. So for those all these blue words, they are not kind of like valid mentions. So we need to identify them as well. Are those mentions valid or not? For example, every student, it didn't refers to any group or specific people. So all those mentions is not valid. So for example, as we said, garbage in and garbage out. So for our language processing, we need to identify which one is the valid mentions, which one is not. So you can use some tools like pre-process our words, process our data, can filter out those kind of like not valid mentions. But another way is more like save more time is just clustering, as mentioned here, just clustering all our data. So for this kind of like, for example, 100 miles, is probably when we do all our clusterings, those words is single as one cluster. So it's not linked with any other clusters. So after we do our clustering process, we will say, okay, this word is kind of a singleton word. It's not linked with any other groups. So we just filter those out and just do the valid mentions part. So kind of like this is the kind of like a save time way to process our mentions. And this is another like build our pipeline system. So as we know, like we probably need to deal with our pronouns, deal with our names, deal with our nouns, use all those like kind of pre-processed system. And then we start to group, we start to build the models like that. So this is kind of like a lot of steps. But finally, like humans are so smart, and we combine everything, all those steps within one system. And Daniel will like explain this like integrated system later. Kind of like build a faster shortcut for our like words in encoding system. And here's another like a definition of our coreference. We kind of like start to learn a new for like a definition is the anaphora, these words. So if we read this sentence, Barack Obama said he would sign a bill. So he refers to Barack Obama, and which is the antecedent of this sentence. And he is the anaphora. So he is dependent on the Barack Obama. And like the first sentence here, Barack Obama and Obama, these words are very like an independent word. So this kind of like a slight different of these two definitions. Yeah, take a look of this chart will be more clear. So like we have two independent words all refer to Barack Obama. And for the anaphora, so he is refers to Barack Obama, and Barack Obama refers to this person. So the words he and Barack Obama, they are kind of like dependent relation. So this is a slight different of these two coreference and anaphora, kind of slight different of this definition. And another like slight thing we need to mention here is not all the anaphoric relations are coreferential. For example, this one, every dancer twists her knees. So every dancer doesn't like refer to any specific people, any specific group. It's kind of like not a valid mentions, not a valid like coreference. And also no dancer here doesn't mean kind of refer to any specific group. So, but there are anaphora words, but doesn't have a specific co-referent relations between each other. So people are probably a little confused about what's the anaphora and the co-reference. What is the difference of them, and are they included with each other or not? So here's like a very brief chart to show the relation with each other. For example, as we mentioned, the pronominal anaphora, which is like the he, refers to Obama, right? So, but if you read this sentence, so we went to see our concert last night. The tickets was really expensive. So the tickets and the concert, they have link because the ticket is the concert ticket. So when we human interpret this sentence, we know, okay, the tickets and the concert have a link together. So this belongs to this Bayesian anaphora. And this is kind of between the anaphora group. And the pronominal anaphora, as we explained, is like he or like she, and dependent on the like Barack Obama, right? This is a pronominal anaphora. So this is a relation of them. And for our like co-reference models, we need to identify all of them. And yeah, Daniel will explain later like how to identify Bayesian anaphora. Yeah, that has another definitions. I know it's a lot. The Catephora is not like a quite used a lot in our like language system, because Catephora is opposite with anaphora. So anaphora is like we trace like the words like backward. For example, Barack Obama will trace back to he, right? But the Catephora is opposite. For example, when we read this sentence, we will say he, his, and then we'll know, okay, he and his is refers to Lord Henry. So we need to trick backward, which is opposite with our usually like linguistic processing system. And this is not used a lot in our language now. And it's also like kind of like disused in our NLP system. So we kind of ignore that. Okay, now comes to a very important part is like how to build our co-reference models. I want to ask, so anyone has any questions, you can mute yourself and ask. Anyone has questions? No? About all those definitions, I know it's a lot of definitions here. Okay, great. So let's move to another part. It's like to build our co-reference models. There are 4 types, and I will explain the basic ones, the rule-based resolution models, which is hand-write, very original one. And then we have a mention pair, and mention ranking, and mention clustering. So it's 4 models. I will explain the first 2. Okay, so we'll come to our the first model is the Hobby's naive algorithm. So when you take a look at this, it's a very gentle like professor. So he gave us like so many steps. So from 1 to 9 steps. And if it doesn't work, you need to repeat from step 4 and it's just go to the following steps. It looks very complex. Let me just explain the basic rule here. Okay. Yes, this one. So he gave us an example of 2 sentences. One is this person is prolific, well-paid, a snappy dresser. And the second sentence is Stephen Moss hated him. So him, like basically it refers to this person, Neil Ferguson. So the rule of the Hobby algorithm is, okay, we find him first. So this is the keyword. We want to find the antecedent of him. And we find here, right? So just mark them as a him. and who is him referred to. So and the step one is we mark this sentence, which is the closest sentence, and we mark as the system here. So the S means sentence one. We just identify this first. Identify what? The first one is the nouns. Okay, Stephen Moss, and this is the verbs hate, and this is the pronoun of this sentence. And after this, we identify everything. So we go upward from him to this sentence, right? This is the first sentence we need to identify and find out, okay, they have a nouns. Here, I'll change another color. The nouns is Stephen Moss. Okay, this is the first nouns of this sentence. So the machine will think, okay, is this sentence a candidate for, refers to candidate accident of this pronoun? And the rule of this hobby algorithm was say, for Stephen Moss, the first noun of the sentence, compare with him. If there has a second noun, we will say, okay, this one refers to him, is the antecedent of this word. But if the first noun, Stephen Moss, between him has nothing of the nouns, we will deny this as the candidate of the antecedent. And if denied, for this case, yes, we deny this because between this noun and the pronoun, there's nothing of between them. So the sentence one, the closest sentence will be denied. And then what's the next step? Is go to go to backward, find the next sentence closer to it. So it's this whole sentence, right? So it's this system, sentence two. So we'll repeat the steps, identify the nouns, identify the verbs, identify like some other nouns. And then we'll go to the first nouns of this sentence. And then find, oh, there's a Neil Ferguson in this sentence. And then we will identify this one. This one is our candidate antecedent. And then like we'll repeat all those steps and find all the antecedent, the candidate antecedent of this words, him. And then we find, okay, and after this, we determine which one's the best one, which one's have highest probability of the antecedent of this pronoun. I know it's it's very original, like baseline of our research is kind of have many steps and time wasting, but it did work for our find the antecedent of our pronoun. And for this part, anyone has questions? Just feel free to ask. No? Okay, great. So we're going to other next part is we know in a lot of case, the sentence is by your knowledge base. Let's read the first sentence. And I have a question here. So she poured water from the pitcher into the cup until it was full. So what is the it refer here? Anyone can ask? You can just mute yourself and tell me what is it refer to?
It's a cup.
Yeah, great. Yeah, Yusa got the answer. That's great. Yes, and then Yusa, probably you can answer me if you read the second sentence, what is the it refers to?
In this case, it's a pitcher.
Yes, that's right. Great. So it all depends on our understanding of this sentence, right? So if it's full without its cup, it's empty without its pitcher, right? So based on this case, the Hobbes a naive algorithm doesn't work. And we have many other cases, for example, case 2, and like the naive algorithm probably doesn't work for this. And when we need to do upgrades of this algorithm. In the current research, we use deep learning to train our models. The basic the theory is we group, we find all those kind of like a knowledge-based sentences, and we group them as like a case to train our models, to train our deep learning models. And then deep learning will find out, okay, if in this kind of like very identical sentences, the machine can identify that. So that's the current research and the current result to process this kind of identical sentences. Yeah, so this comment is like the Hobby's algorithm is they did work for some sentences, but it's kind of naive to process some like very identical sentences, like some knowledge-based sentences. Okay, so we'll come to a second part is our improved models is the mention pair. You can take a look of this is a result of after our clustering our data. So I vote for Nader because he was the most aligned with my values, she said. So when we interpret this sentence, Nader and he is one group, is within one cluster. I, my, she is another cluster. So we identify this whole sentence into two clusters. This is a result of this mention pair system. And from this one, we see is quite accurate. It's good. And let me explain the detailed steps of this mention pair models, how we build that. Step 1 is we find all the mentions. Of course, like I, Nader, he, my, she, it's all the mentions. And when we see here, this 5 words, we need pair of them. For example, she as an antecedent, and we pair my with she, he with she, and so on. Just create all the pairs, all the possible pairs with she. And then you see, after this, we have different pairs now, right? So we identify as P, MI, and MJ. And we then use our machine to say which one is positive, which one is negative. For example, if she with my, which is a positive, and we mark as 1. And she and he, which is not a kind of like a, for example, he is not like antecedent of she, so we mark as negative, can be 0 or can be -1. And then after we do all of pairs, we finish this part, just pair all the possibility of our words, and then encode with 1 or 0. Yeah, this is the negative part. And then we build our loss functions. So we need to do a little bit interpretation of this loss functions. Let me just change to this one. Okay, so this is the loss function of the cross entropy. So when we interpret this one, so y, I, and j represent the binary result. So if the positive, we say is 1. If it's negative, we mark as -1 or mark as 0. So we use this to do our binary classification. And the log P here, the P here is the probability of each pairs. So for example, give us like if it is the negative, what's the probability of this pair? And then we can find, okay, if the high probability, it probably is positive. If it is low, for example, 0.1 or something, we mark as negative. And then we use this one to go through all our mentions and like antecedents. here, for example, just go through that. So for example, I equals 2. So it's from nada, right? Which is I here. And how we find the pairs? We just go to J equals 1. So, okay, nada and I as one pair. So now it comes to I equals 3. So it's here. So J will be 1 and 2. So just pair I and pair nada with he. Yeah, and so on. And we finish all the pairs and then count our loss functions like that. Okay, so when we have our like loss functions, we need to set a bar, like what's the threshold of those kind of like loss functions. It's kind of sensitive. For example, just yeah, it's here. So the threshold you can set here is like for example 0.5, but how to set the value of your threshold is so important. Sometimes you can set a 0.5 or 0.8. It's probably is by experience or by a previous data set. And after we set our threshold, and we already done with our clustering. So if bigger than 0.5, we set as positive pairs. If smaller than this, we set as negative pairs. You see, this is the result. So we got our different clusters. But there has some like transitivity of this module. For example, we identify I, my, she is one group, but I and my, these two, it could be a pair, could be like a same as a pair as well, because it's kind of a transfer, the clustering. So this causes a problem is if you set your threshold slightly different, and that it kind of like have a mistake. The group he and my as one group, then these 5 words are identified as same cluster. So that is wrong result. So this mentioned pair it has disadvantage is very sensitive to how you set your threshold value. Yeah, that's a positive advantage. And another advantage is, for example, this is a text, it's a paragraph. And what we're trying to find out actually is he refers to nada. We need to find out, okay, like he, his, him has all pair with he. So from this graph, you will see if we do pairs, we need to find out the he pair with so many words, and they're all positive. So it doesn't mean to us, because we only need to find out the most make sense pair, which is nada and he, right? We need to find out the relation with each other. We only need to find out, okay, this nada and he is within one sentence, and we only need to find out, okay, this pair is makes sense, and other pairs doesn't make sense to us. It doesn't help us to help on the interpretation. So this is the kind of like this advantage of mentioned pairs. We only need to find out the most important, most making sense pair in this whole paragraph. So this is here, and Daniel will explain later, like say, it will give a rank of each pairs and find out the most important one. I will pass to Daniel on the mention ranking. And before that, I want to check anyone has any questions on those topics. You just can mute yourself, unmute yourself and ask. Okay, it seems the voice is not clear. Okay. Any questions? Okay, so I'll pass to Daniel on the mention ranking.
Oh, sorry. Okay. Let me just.
Jenny, you're muted.
Can you hear me now?
Yeah, now works.
Oh, okay. Oh, since I muted myself, sorry. So anyway, so we are going to continue from where we left over. So Yuyao actually mentioned one of the most important problems with the mentioned pair model. That is, we have too many, sometimes we have too many references right here, co-reference right here. Like he can be linked to all those kind of words right here. But does that really matter if we just link he to his or he to him? Not really, right? So why not just find the most important linkage among all the co-references, which is the anaphor right here? As long as we know that Nader and he are the same person, then we know that Rafael Nader and he, his, him are going to be the same person. So that's a core idea of the mention ranking. That is, we're going to rank all the anaphor and co-reference linkage, and then we are going to pick the one with highest score. So after speaking, assign, what do we do is actually assign each mention its highest scoring candidate antecedent according to the model. That is, we're going to find all the antecedent of the mention. Like for he, all those are just like, antecedent. And we're going to find the highest one, the score with the highest, like the one with the highest score over there. Okay. So what do we do first is like for each sentence, we're going to add an A, which is noun value in front of the whole sentence, because we, especially when we do, for example, suppose we start from here, we do this as a mention. We do not really have any antecedent. So we need some kind of like a virtual antecedent to start with. So that's basically what we do here. So the basic idea is like, for example, suppose now we take she as a mention, and all those are just like antecedents. Okay, so what do we do is like, we're going to pair each of them, and then we're going to calculate, the pair score using softmax function, and we're going to find the one with the highest one. For example, the highest one is I and she. Then we're going to put that, we're going to link that to she, and we're going to banning others. We're leaving anything else. We don't actually think about other stuff anymore. So that's a core idea of this kind of like mention ranking models. So what we want to do now mathematically is we actually want the current mention MG to be linked to just one. It could be anyone, just one of the candidate antecedents that's actually co-referent with. Okay. So the loss function is still the same. It's actually still the same as before. So G refers to the candidate antecedent, and if it is the highest one, or if it's a true antecedent that can be linked with the mention, then it's gonna have a value 1 here. Okay, and this is just a score that matches or actually link the mention to one of its actually previous antecedent. So the core idea is like, why do we actually still use the sum? Why do we actually just do just individual kind of like a scores here? So the core idea is that even we use the sum, suppose one of these kind of like pairs has a high score, which is 0.9, and others just have 0.1, 0.01. That doesn't really matter because the sum is still going to be high. So it doesn't hurt if we use the sum. So we're going to stick actually to the sum for the loss function. And this is just the same as before. So for each mention, I refers to the mention. For each mentions here, we're going to loop through all the antecedent and try to find whether they're the true one or whether they're not the true one, and try to find their kind of like pair scores. So you can interpret this as a logistic regression. It's actually pretty much it's actually the same as a logistic regression loss function. Okay, so it's binary. It's either 1 or 0. Okay, so how does the classified or the or the ending or the result of this kind of model look like? That is, previously we have like with mention pairs, we're going to have this, right? One mention is going to be linked to multiple actually antecedent, but now we don't have that anymore. One mention can only be linked to the highest or the best antecedent, and then it's going to link it to another antecedent. It's not like she linked to my and she linked to I anymore. It's not like that anymore. It's only linked to one of these actually one of these antecedent. So that's a difference. So to summarize, mention pair models is gonna match one mention to multiple coreference, no matter how many we have over there. But for the mention ranking model, what we only care is the best or the only one antecedent that has the highest score. So we only link that mention to one of those potential candidates over here. Okay. So in that way, the transitive closure has been broken out. It's more like a tree structure. So previously, what I mean by that is like previously we have she, it can be linked to I, it can be linked to my, right? So you can group those two into a cluster right here. But now it's more like a tree structure. She can be linked to my, and my can be linked to I. Okay, so the transitive closure has been broken out. In that way, even if you actually wrongly classify, one of suppose those two are classified together, you wrongly classify those two, it doesn't generate that huge kind of problem to us as previously mentioned in the mention pair model anymore. Okay. So another model which so far is actually is a cutting edge, is most like it's actually the latest kind of model has been invented, which is also the best performed model in this area. It's called end-to-end model. So as try to recall previously when we talked about the pipeline model, which has a lot of steps or different kind of procedures. Either we have to do a part of speech tag, or we have to do name entity recognition, and after that we are going to do a second step as clustering. So someone's asking, why not just propose a model that actually does everything from the beginning to the end, just one step, so we don't have to actually go through several steps at a time. So that's the end-to-end model right here. So to summarize a little bit, this model, first of all, it uses LSTM. Second, it uses attention, which is a really special feature of this kind of model here. And overall speaking, it's actually a feed-forward neural network with those two. And the unit of the input or the unit of the output is not a one single word anymore, especially the unit of output is not a one single word. It's like a span of the text. It's a span of text. So a span is just a contiguous sequence of words. For example, this word, one word can be a span. General Electric can be a span. General Electric said can also be a span. So it depends on how long the span is going to last. So you could have a span of various lengths over there. Okay. So how the model was constructed. So step one, we're gonna actually tokenize every single word, and then we're gonna find some kind of word embeddings for each word. You can do your own word embedding again, or you can just use some other pre-trained word embedding, doesn't matter. So every single word here is gonna be an input to this model. And after that, we're gonna feed all those kind of like word embeddings into bidirectional LSTM. So why is bidirectional LSTM? That is, we try to actually read the sentence from left to right, but also from right to left. because sometimes, we do need to find some subsequent word which can be linked to a previous word, but it could be the reverse. Okay, so the next step is we are gonna actually encode the result or the outcome of LSTM a little bit more using span representation. That is, for example, General Electric, we are gonna put those words together and make it a span, then we're gonna encode that. Or it could be, for example, the postal service, those 3 words can be actually put together as a span, then we're gonna encode that. So now the question is, how do we actually encode a span? What kind of procedures do we have to go through to encode a span? So let's take this example, the postal service, okay? So a span, the encoding of the span is gonna take several different features. So the first feature, the first static feature is actually the starting word as the ending word of the span. So the starter word for this one is actually the, and the ending word is gonna be the service, right? So those 2 features is gonna be the first set of feature we use to do the span representation. The second set of feature, which is the most important set of feature, which is called attention-based representation or attention feature, we're gonna use to actually do the span, which I'll explain later, just like in 20 seconds, in 10 or 5 seconds right here. And we also have other kind of like additional features. Those features could be, just like you all mentioned previously, it could be the order of the sentence, the order of the words. Is this word subjective? Is this word objective? Is this a verb? Is this noun, or so on and so forth? Okay, so now let's go to this step a little bit more. What does attention actually, what kind of role does attention play in the span representation right here? So suppose we have this kind of like example, the postal service right here. We need to find the mention of this span, right? Or we need to find the header word. It's actually those 2 are the same. Or the most important word or the keyword of this span. Keyword of this span. That is the postal service. Which word should be the most important word of this span right here? That's a question we cared about, because we need to find a mention, then we can link the mention to other references or to other kind of like, anaphors or antecedents, right? If we can't find a mention, we can start from the first step. So what the attention does here is, for each word here, it's gonna find the linkage of this span representation and that word. That is, for this kind of like the postal service, how much importance should we attach to the, or how much importance should we attach to postal? How much importance should we attach to service? Okay, so that is, we're gonna re-encode the span, or we re-encode the span of the words towards, or biased towards one specific keyword right here. So now the question is, what is the keyword, or what is the mention here? Of course, it's a service, right? It's a service. So this would be the one with the highest like attention score. Okay, so as with respect how to actually calculate attention score, it's actually the same as before, which I don't think that we can mention that anymore. So I think if you want to know more, you can go back to the sequence model. There's more details over there, but I would say the core idea is actually try to find the weight of each kind of word relative to those kind of span, and then we're going to do the weighted average of this kind of like each word within this kind of span. For example, 0.1 times the plus 0.1 times the postal plus 0.8 times service, right? After we do this, then this span is going to pay more attention to service right here, right? So here actually explains why we actually use a span. So if we actually try to use attention to find the mention without span, suppose we just do every single word. Suppose we don't have this step. We just do every single word. I just give you one word, general. Can you tell me that's a mention or not? Actually, you can, because it's not relevant to any other words. you have to find the context of word to figure out which word is a span, which word is a mention, sorry, which word is a mention. So that's why we actually care about the span. That's actually the most like smartest idea of this kind of whole model right here. So after we have the span, then we're going to represent each span as a S. Okay, so we're going to score every pair of spans. We're going to score every pair of span and see if they're coreferent or not. So this kind of score has three most important like parts. First is like a subscore. This subscore is SMI for span I. Basically, it asks you, do we have the mention or do we have the mention words in this span? And second kind of like score is the same as the first one, but it's asking for another one. Do we have any mention or do we have any keywords as the mention in this kind of span right here? A last component is another score that tells us, does those two span actually look like they are coreferent or not? Okay, so it has three most important components listed right here. So specifically, again, each step component, again, use attention as, as a way to calculate this kind of like a, subscore right here. For example, for as mentioned here, for I is actually another weight times, the representation after you finished all the forward feed neural network right here. So which is, it's kind of similar as this one here, right? Attention score. So that's another attention score. That is, for each kind of like I mentioned here, do we really have a word that actually has a high, attention score, or can we really find the word which is a mention or not? So that's one score we use here for coreference score between two spans. Another one is, again, it's going to use attention here. This is another example just like this again. So basically, for any two spans, you're going to do a feed forward neural network using each span as a representation, and also their dot product as another feature, and a bunch of other features. And after you finish that, you're going to train a weights and try to multiply that weights with this feed forward neural network representation of two spans, and try to get attention score right here. Okay, so that's basically how the model works. But the key, or the most kind of like concern, most like a biggest concern, or the biggest flaw of this kind of like model is that we could have any inline spans. We could have many different spans. Like those two could be a span. That could be a span. That could be a span. That could be a span. So you could have unlimited possible spans over there. So if we considered every single spans over there, then the dimension is going to explode. The computation task is going to be huge. So the running time is going to be very long. So to solve that kind of problem, we have to do some kind of pruning. So basically, we have to take off some kind of like spans which are not that relevant or important to find a mention. For example, those two, see, stat z are not actually, considered as a potential span, because stat z, it doesn't have any useful information. It doesn't contain any mentions. It doesn't have any coreference relationships, right? So those two shouldn't be used as coreference, and it is not used as, kind of like a span right here, right? So we don't have this one, right? So that's what we call pruning. And this is just based on domain of knowledge, based on the common sense, like what type of like spans you want to actually get rid of. Okay. So another model, which is very similar to the traditional clustering model, is called like mention clustering model. This model starts with each mention as its own singular cluster, just like a k-means. So it's going to merge the cluster at each step and use a model to actually score this cluster and see whether that merge is good or not. So let's take an example just like this one. Google recently, blah, 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 the company announced Google Plus, blah, 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 the product features. So basically we have four mentions. Okay, we have four mentions. And what do we do first is like, we're gonna list each of the dimension as, a cluster of itself, okay? So next, we're gonna consider the pair. For example, we can consider cluster 1 and cluster 2. If we put them into a pair, what's the score gonna look like? What's the span score gonna look like? So it's 5. Suppose the threshold is 3. 5 is greater than 3. Then yeah, let's merge this. This is a good cluster to merge. So to the next step, then those two has been merged to cluster 1. So we still have another 2 clusters. So next step could be, let's look at those 2 and see if we merge them, what's the cluster score? Turns out it's a 4, which is greater than 3. So yeah, let's merge those 2 as well. So we now have 2 clusters with 2 kind of different kind of like a span in each cluster right here. So next step would be, can we merge those 2? Suppose we can. Let's calculate the cluster score, which is -3, which is smaller than threshold. So we don't merge them. So basically that's the end of the story. So we have 2 clusters right here. Okay. So this is exactly just like a k-mean. Basically you calculate the similarity between any 2 data points. And if they are the same, if they are close enough above the threshold, then you just merge them and into the cluster. Okay. So yeah, but actually, in this model, we don't do that as a naive way in the k-means. We do that more like neural network way. So basically, suppose we have the 2 clusters right here. Suppose we try to merge the 2 clusters. Then we're going to consider every single pair of every single kind of spans between the 2 clusters right here. So those are all the dimension pairs we have. Then we're going to code each of them into a dimension pair representation. And next part, we're going to do the clusters. Suppose we're going to actually put those 2 and those 2 or any 2 of them into a big cluster. And we're going to actually score this big cluster of all dimensions, all of the dimension pairs right here. And then we're going to judge whether that is greater than threshold or not using softmax function. Okay. So that's basically how the clustering works. But in more details, you should actually go back to the slides, and I think there's more details over there. But the basic idea is like here, like how we actually do the clustering. Okay. So the next part is actually evaluation. So after we finish all the coreference resolution, how do we actually evaluate our work? Did we actually do a good job, or we did a mediocre job, or we did a bad job, right? So there are different ways or different metrics you can actually use to do the clustering evaluation, like MUC, CEAF, LEA, B-curve, and blend. So I'm not gonna actually tell every single metrics to the group member, because it's gonna cost like maybe another hour. But usually what we do here is we usually just report the average of the few different metrics. Suppose you select those 3 right here. You either do a arithmetic average, or you can just do a like square root or kind of cube evaluation, or average over there. Okay, so I'm just going to take B curve as one of the like example to explain how the metric works. B curve is actually the most basic one, or it's actually the easiest one. So basically, for each dimension, B curve gonna actually compute a precision and a recall. Then we're gonna average the individual precisions and recalls for each observations over there. For example, suppose we have the 2 clusters right here, that one and this one here. Okay, and suppose the red represent gold cluster and gold, and this is another cluster right here, cluster 1 and cluster 2. So if we actually look at this point here, we try to find the precision. Then the precision should be 1, 2, 3, 4 divided by all 5, right? And the recall should be 1, 2, 3, 4 divided by 1, 2, 3, 4, 5, 6. All the potential red points right here, right? That's a recall. So should I actually mention what a recall or precision is, or you guys already know what a recall precision is? That should be the basic definitions for a classification. Okay, let me just write here. So precision is true positive divided by true positive plus false positive, and recall is actually true positive divided by 2 positive plus 4 negative. Okay, so that's basically how you calculate the precision and recall. Okay, so after you calculate all the precision and recalls, then you are actually going to weight them by the number of the observations over there, and then you are going to take the weighted average and try to calculate that as overall precision, overall recall over here. Okay. So another kind point I want to stress right here is that for precision and recall, they have a trade-off relationship. So as long as the precision increases, the recall is going to drop. Or if you have a high precision, then you must have a low recall. Okay. So in order to solve that kind of problem, most of the time we don't actually just use the precision recall. Most of the time we just use the F1 score. Okay, we just use the F1 score. Okay. So that's how you can do the evaluation. For other metrics, you can just go back to the slides and find more kind of details over there. Okay. The last part is actually the model comparison. So this table summarizes all the models we mentioned in this lecture and try to do 2 different coreference resolution tasks using 2 different languages, English and Chinese, and try to actually figure out which model performs the best. Okay, as you can see, the rule-based or the handwritten model, which is the most basic model, it's actually doesn't work that well, right? It's actually pretty much at the bottom rank of all the models over here. And the best performing model so far is actually the latest one, end-to-end neural network model. And other than that, you can choose a neural classroom model, which performs good enough, but not as good as the end-to-end model here. But you can always use this one here, the rule-based a system as a baseline for sure. Okay. Okay. All right, that's everything about today's lecture. Any questions so far?
Hi, Daniel. Yeah. Thank you for the presentation. I have a little question about the span there.
Yeah, sure.
So you said how we have so many words, probably can go to that slide.
Sorry, what's that? Say it again.
The span, probably the one before. Let's go back.
Yeah. Oh, this one here. Yeah.
Yes. So for the last ones, you said we have so many words here, and if we just check each, so there are too many groups. So we need to identify which word is a valid link. Which word, for example, the surface, that one is a valid kind of a phrase. So we need to screen out which is not valid. So how we screen that? It's is there any?
What I can come up with is actually try to use a different other sub models. For example, you can use entity recognition, right? Name entity recognition. You can do an NER. That is, you can just do here. Before you do the span representation, you can do an NER. Right? Or you can do a part of speech tag.
Just
right. You can just borrow, before you do the representation, span rule here. Try to figure out which are the name entities, which are the organization's name, which are the people's name, or try to find a tag for part of a speech. Yeah.
Then we just screen out a lot of.
Just screen out others. Yeah.
Okay, great. Thank you.
Hi, Daniel. I have a question on the evaluation matrix. There are many co-reference evaluation matrices here. So I think they are mostly a cluster evaluation matrices.
Yeah.
So I was just wondering, your application might involve some clustering. So are there any one specific that are mostly used, or do you have any comment on that part?
I would say the industry always starts from the basic one. So we always start from the simplest one, which is that one. So so it's more so I would say in this way. So for example, we have different layers. I would say, layer 1 matrix, layer 2 matrix, layer 3 matrix. So we always start from the basic one. This one could be F1 score. Okay. If we pass that, if we pass this, then we can go to a next step. See, we have a better, higher, or see, for example, theoretical afferent score, right? Or theoretical precision recalls, right? So we can check this one as well. If we pass that again, we can go to the last one. So it depends. It depends. We always start from the basic one. If the basic one is really satisfying enough, then we can actually extend it and try to figure out a little bit more. But if we already failed the first layer, suppose the F1 score is super low, then there's no point to go to other complex, like matrix over there for evaluation. Because if this one doesn't work, then for the more complex one, it's basically more likely not going to work as well. Yeah.
Okay, cool. Thanks.
No problem. Any other questions? Nope. Okay. Just stop sharing my screen right here. Okay. So that's, oh, sorry. I think I just missed the chats. Okay. Okay. All right. I guess that's everything for today. If you want to sign up for next week's lecture, please let me know as soon as you can. Like better before Tuesday or Wednesday, because at least we have plenty amount of time to actually work on the lecture. So feel free to actually join us for the next lecture. And thank you all for attending today's lecture, and hope you guys enjoy the rest of the day, and see you guys next week.
Thank you, guys.
Thank you. Bye.